The next thing we're going to do is talk about symmetries of, in this case we'll do rectangles, but these symmetries can be used with any kind of regular polygon, so like a regular triangle, an equilateral triangle, a square, regular pentagon, regular hexagon, and so on. Now, what do we mean by symmetries? Well, we're going to want to talk about symmetries so that they have these four properties. And these will become more clear as we do examples, or as we do this example. First one, combination of two symmetries is a symmetry. Possibly the same one, possibly a different one. The next property, we want a null symmetry. The null symmetry is just going to take our rectangle and leave it alone. The third, an opposite symmetry. So if you have one symmetry, you're going to want something that will, in a way, undo that symmetry. And the last one, the symmetries are associative. So that means associative like with numbers, A times B times C with parentheses on A and B is the same as you could throw the parentheses on B and C. In other words, you can do them in whatever order you want. Now, these will become more clear as we do an example. Well, hopefully they become more clear. I think they will. So let's draw a rectangle, perhaps golden. And let's label the 4 points on that rectangle. Now we're going to find symmetries. And we're going to break these symmetries into 2 different symmetries. We're going to call them rotational symmetries and axial symmetries. Now a rotational symmetry, we're going to want to rotate this rectangle so that it has the same shape and is in the same direction. An axial symmetry means we're going to flip it over an axis, and we want it to have the same shape. So let's first talk about rotational symmetries. Well, if we rotate it 0 degrees, what happens? Well, we get this rectangle. 1, 2, 3, 4. So that is a symmetry because that is the same shaped rectangle, and it is in the same direction. That 0 degree rotation will form this null symmetry because it's not really doing anything. What happens if we rotate it 90 degrees? What happens if we rotate this 90 degrees? Well, we could do it in either direction. Let's say clockwise. 90 degrees clockwise would form this rectangle. Which one would have formed? We would go 1, 2, 3, 4. If you rotate it 90 degrees clockwise, it forms that rectangle. We are not going to include that because we want our symmetries to preserve the shape and, well, the shape, let's say. And the direction, I guess, was what I was saying a couple minutes ago. So this is still a rectangle. It's still the same size, but it's in a different direction. We are going to exclude that. So I'll put an X through that, and I'm going to erase it, actually. In your notes, you could leave the X through. What if you rotated it anything between 0 and 90? Well, if you rotated it between 0 and 90, your rectangle would be tilted. So you rotate it between 0 and 90, say you rotate it that much. Well, that's not going to have the same shape and direction. But what if you rotated it all the way around? Well, halfway around, I guess I should say. Instead of 90, you went around another 90 to 180 degrees. Well, if you rotate it 180 degrees, it's going to be the same shaped rectangle in the same direction. You rotate it 180, now 1 is going to be down here, and then 2, 3, and 4 fill it in. So if you rotate it 180 degrees, you get the same rectangle in the same direction. So all of these symmetries, we're going to want the rectangle to still look like this. This, like a rectangle pointing up like this, will not look like it, but this will. And a 0 degree rotation does that, a 180 degree rotation does that, a 360 degree rotation would also do that. But that would give us the same as 0, so let's leave it as 0. Now, axial symmetries, maybe I should, I might need more space. Maybe I won't, let's see. In axial symmetry, the way I like to see them is by drawing a vertical or a horizontal or a diagonal line, any straight line through this, and rotating it about that axis. So what I'm going to do is draw the line over here and draw the result over here. What if we draw this line? That vertical line right through the middle. And what we want to do is flip it across that axis. So it starts like this. We're flipping it across that axis. So it starts like this. It's flipping across. You can imagine, like, I don't know, it's like a sign of some kind in here. It's not fastened properly, so it flips around to the other side. Where do the 1, 2, 3, 4 go? And what happens to the shape? Well, the shape is still like this, but now 2 and 3 are over here, and 1 and 4 are over there. So that's one thing we can do. What if instead of going across that vertical line, what if we did a horizontal line? So we have this down here, and we flip it across that horizontal line. Flip it across that, well, it's going to be the same type of rectangle. But the numbers are going to be in different spots. We have 4, 3, 1, and 2. So we saw here 2 axial symmetries. Now, are there other axial symmetries? Well, what would happen if you, instead of going a vertical line, what would happen if you did a diagonal line? If you tried a diagonal line, what would happen if you flipped across that diagonal line? It would go like that. You flip across the diagonal line, this straight line of this length is now going to go like up here, and the rest is going to go down here. And you're not going to get the same shape because it's a rectangle. You flip across that diagonal line, it's going to turn into an upright sheet of paper rather than a portrait sheet of paper rather than a landscape. So a diagonal axial symmetry does not work for a rectangle. For a square, it would. For a square, if we were talking about these symmetries, there would be more in each case. But here, for a rectangle, we just have these 2 axial symmetries and the 2 rotational symmetries. So notice, as a conclusion, I'll just say there are 4 symmetries of a rectangle. There are 4 symmetries of a rectangle. Now, let's talk a little about these properties. Combination of symmetries is a symmetry. Meaning, if you, say, rotate this rectangle 180 degrees and then flip it across an axis, it's still going to be the same rectangle. The numbers will be in a different order. If you flip across a horizontal axis and then rotate 180 degrees, it's still going to be a rectangle. So combinations of any of these 2 symmetries is a symmetry. The null symmetry we already discussed. That's the one that does nothing. It's a null operation. An opposite symmetry. Well, in this case, what are the opposite symmetries? What's the opposite of 180 degree rotation? So we start here, go 180 degrees. Opposite means another symmetry that brings it back to its original state. So you start like this, go 180. How do you get that back to the original state? Well, another 180. Start at 0, or not start at 0. Start like this, rotate 0. How do you get back to the original? Well, you rotate 0 again. And with the axial symmetries, you also just apply the same symmetry. Flip like this. How do you get back to the normal? Well, you do the same flip. What would happen if you do both? If you apply both axial symmetries, you will not get the same result. If you apply both axial symmetries, you'll get what? This and then this. So it would be the rectangle with what? 4, 3, 2, 1. So actually, maybe I'll just observe right now as a side observation, this symmetry operating on this symmetry results in a 180-degree rotation. That's actually a good thing to justify in your head. I'll say it again. Flip and another flip. So apply this flip, then apply this flip. It's the same as this. So try that. Try writing that down, or try even labeling a piece of paper somehow. This flip and this flip is the same as that. Definitely a good thing to know. That's a nice property in higher level math. Yes, higher level math, an entire branch of math could actually start with this discussion. A relatively advanced, very advanced, generally the most advanced undergraduate math class could start with this exact discussion. Symmetries are associative, and the associative property is kind of annoying, but if you do one of these, then this, if you do this, then that, it's the same as doing this after doing that, then that. I mean, it's the associative property. ABC equals ABC with the parentheses moving around. I'll just say it works here. So we discussed these properties using symmetries. Well, we discussed symmetries with these properties in mind, and we used these symmetries and these visuals to talk through these properties. These properties form a structure in math that's very important. It's a structure called a group. And we'll define that a little more formally. But let's talk about these symmetries using numbers and operations. Let's use, as an example, I'm not going to write all the details right now. Let's use real numbers, and let's use the property addition. So here, instead of rectangles, we're going to work with real numbers. Instead of symmetries, well, maybe I'll say our symmetries are the operation addition. What do these properties look like with that? Combination of two real numbers gives us another real number. Well, a real number plus a real number is a real number. Property 1. What about the null symmetry? Real number plus something not doing anything to it. Real number plus 0 does nothing to it. So there's our null symmetry. Opposite symmetry. Real number plus something else brings us back to 0. In this case, the opposite would be the negative number, because like 6 minus 6, 6 plus negative 6 equals 0. That's what we mean by opposite in this context. Symmetries are associative. 1 plus 2, then plus 3 is the same as 2 plus 3 plus 1. So let's define this a little more formally. So, more formally, we define a group. A group is a set together with an operation. So it's a set G and an operation which we'll call star. Now, the star, the operation, applies on pairs of elements of G. So with that last example, our operation was addition. Addition on real numbers. But here, in general, a group is a set G and an operation star between pairs of elements of G, and the star satisfies these properties. The star and the group satisfy these properties. First, closure. For two elements in G, this symbol right here, it's a kind of like an E type thing, but in math it's read in. And it's just used to describe things that are in a set. So if two numbers are in the set, then the one operated on the other is also in the set. 2, identity. There is I, that's a capital I in G, with I operating on A being the same as A operating on I being the same as A. So in that example with the real numbers and addition, 0 functioned as our I. Now in describing a group, immediately jumping to exactly what I is quite important. So for the real numbers with addition, our last example, 0 was I, because 0 plus a real number is the same as a real number plus 0, and it's the same as that real number. We made I star A to equal A star I equal A. 3, inverses. If A is in G, so if there's some element in G, there's an A inverse in G, which we'll write as A to the negative 1 in G, with A operating on A inverse being the same as A inverse operating on A being the same as I. So with our example with the real numbers and addition, the inverse was the negative number. So 3 plus negative 3 was the same as negative 3 plus 3 was the same as 0, the identity found in part 2. And the associative property, if you have 3 elements in G, then 1 operating on the other with parentheses around it, operating on the third, is the same as if you go in the other order. Now, we describe the real numbers with addition. Real number plus real number is real number. Real number plus 0 is the same as 0 plus the real number is the same as our real number. Real number plus its negative is 0, and real numbers with addition are associated. You can add in whatever order you want. Let's look at a couple more examples. Let's look at the positive real numbers. So let's let G equal the positive real numbers, and let's let our operation be multiplication. And I could have written with X. I'll just write the word multiplication. These positive real numbers form a group. Why? Well, let's go through the 4 properties. Positive real number times positive real number. Is that another positive real number? Yes. Positive number times a positive real number is another positive real number. So, closure, satisfied. What about the identity? Is there a number so that that times some element is itself? Or is that element, I should say. Is there a number such that it times any element is the same as any element times it is the same as that any element? Yes. The identity equals 1. 1 times anything is that anything. And anything times 1 is also that anything. Inverses. Inverses. So to figure out what the inverse is and when it exists, you need to know what the identity is. We need to know, in order to find the inverse, what this equals. In our first example, the identity was 0 with real numbers and addition. So we knew we had to make A star A inverse equal A inverse star A. We needed to make that equal to 0 in the first example with addition. But here, with multiplication, in part 2, the identity was 1. So we need, given an element A, we need to find an A inverse so you can multiply them together and you get 1. Well, how can you find that? Well, what if A equals 2? 2 is a positive real number. 2 times what equals 1? Two times what equals 1? 2 times a half equals 1. I'm going to erase what I just wrote there. Why am I going to erase what I just wrote there? It looks like I'm using the exponent to rewrite that fraction. This is not a result of exponents. This notation there is A inverse is actually a result of this property, actually. So if you have 2, you need 2 times a half. It's reciprocal. If you have 7/8, how do you get to 1? You multiply by 8/7. It's still a positive real number. So I'll say the inverse of A is 1 over A. And for the last one, for associative, well, real number time, let's just do an example. 2 times 4 times 3. 2 times 4 is 16. 16 times 3 is 48. I forget my numbers. What did I say? 2 times 4 is 16. Yeah, good job. 2 times 4 times 3. 8 times 3 is 24. On the other side, 2 times 4 times 3. 2 times 12 is 24. So I'll just put a check mark. Associative works. With these, generally, talking about the identity and the inverses are more difficult than the other two. And usually the other two are just, yeah, it's true. Real number plus real number is real number. What more can you say about that? Real number times positive real number times positive real number is a positive real number. So let's look at one more example. What about this set? This is a set you may have seen before. Whole numbers, all whole numbers, all positive whole numbers, all negative whole numbers. So in other words, 0, 1, 2, 3, 4, and so on, and negative 1, 2, 3, 4. I forgot a negative sign here. Negative 1, negative 2, negative 3, negative 4, and so on. This is called the integers. It's called the integers. Yeah, why not? I'll tell you. A shorthand abbreviation is a capital Z written like this, with an extra line on the diagonal, and then I always cross my Z's, so I cross this Z as well. Capital Z, shorthand for integers. Something to do with the German language and their word for integers. So we have the integers as our set. Let's take addition. So let's say integers with addition. Is this a group? And why is it a group? Is it closed? Well, here, remember, we want integer plus integer. Is an integer plus an integer another integer? Well, it's just a whole number plus another whole number, maybe with some negatives on it. So yes, that is closed. What about the identity? What is the identity? What is the number that we operate on an integer and it doesn't do anything? Because the identity, with our operation, just operates on an integer and does nothing. Integer plus what doesn't change it. Integer plus 0 doesn't change it. So here our identity equals 0. What about inverses? Is there an inverse? So given an integer, can we add something to get us back to 0? Given an integer, can we add something that gets us back to 0? Yes. So I'll say it's negative. Because negative 4 minus negative 4 is 0. Ah, jeez. Negative 4, I said that completely wrong. Negative 4 plus 4 is 0. 3 plus negative 3 is 0. So yes, there is an inverse. And associative, again, you can add in whatever order you want. Now what about an example where it isn't a group? How could that go wrong? Well, this is an example of something that is not a group. The real numbers. Real numbers abbreviation is a capital R with a bold vertical line on the R, and that's written with a double bar. The real numbers with multiplication. So I'll just say real numbers with multiplication, not a group. It's real numbers with multiplication is not a group. Why? Well, let's go through the properties. Closed. Real number times real number. Yep, that's a real number. Identity. Well, again, identity equals 1. Identity equals 1 because 1 times real number equals real number times 1 equals real number. Inverses. Well, let's jump to associative. Associative, yes. Inverses. Well, I'm going to tell you, I told you this is not a group. 1, 2, and 4 worked, so 3 mustn't work. Why doesn't 3 work? Well, let's look at the phrasing of 3. If A is in G, then there is A inverse. That brings us back to the identity. If A is in G, well, let's translate that to the example we have. Given a real number, there's another real number where you multiply and get back to 1. Well, that works for a lot of them. If A equals 5, well, then you let the inverse be a fifth. If A equals root 5, you let the inverse be 1 over root 5. But what if A equals 0? If A equals 0, there's no way you can multiply 0 by something and get back to 1. So the fact that 0 is in there screws everything up. If we took 0 out, so if we had real numbers without 0, it would be a group. But the fact that we have 0 in there prevents it from being a group. All it takes is one bad element and it's no longer a group. So with these, this video might be worth looking at a second time. Because it is, in many ways, a new language, this group discussion and these symmetries discussion. So real numbers with addition formed a group, positive real numbers with multiplication did, integers with addition did, and those symmetries also did. They're good to understand. And this one didn't because of 0. So let me know how the examples go. There are a couple worksheet examples, a couple homework. Let me know if it makes sense. Because this group stuff is not easy. I think it's reasonably difficult. When I first saw it, I thought it was pretty difficult.